Good evening. Welcome to this episode, Learning Amiga Assembly with Docster. I included the name of Docster because he also submitted, while I was doing this stream, not this stream, sorry, when I was doing the notes, he also submitted his own examples. So I said, okay, let's, name the stream after him. So, yeah, that's why it is Learning Amiga 68000 Assembly with Docster. It's a very beginners series. I mean, I'm basically covering 68000. Besides that, I was hoping, as most of you know now, that I would have loved to stream from the Amiga, as you can see it on the upper right hand corner, but unfortunately I forgot a cable in UK and I cannot stream from it. So there you go, my luck. I am in my other, let's say, studio. No, that's a joke. I'm in my other country, which is Malta, so yeah, I'm streaming from there instead of UK. And of course, I have lots of things here, but that cable is not here. Anyway, so let's go to the usual ritual. So, the browser. There you go. So, all I ask is for you to follow, subscribe, like my YouTube channel. It's the only way I know of sharing things to others, and let's say YouTube likes when people join and shares things more. So that's why I am saying that. I remind you that under each video there is this thing, show more, which will give you access to more things. I have the Phase 101 Facebook page, which is like my blog right now. I really would love to change this, and my aim is to change this to be I mean, I will keep this, but of course I would like to have a web page because it's very difficult to find things on Facebook. It's okay to, you know, see the last few, but if you had to say, okay, what did I do a year ago, you cannot really see it. So I need some kind of blog. I have the Facebook Phase 101 group. So join, subscribe, like also this group, and same the Commodore dev group. So join, subscribe, like, whatever. Every little bit helps. So if you do not like, sorry, if you send me messages on Facebook, I do tend to be slow in replying on Facebook because it's not something that I look at all the time. But if you message me on Discord, I reply a lot more quicker, if not instant. Besides that, some people do not like, so please join my Discord group, the Phase 101 group on Discord. You can see links always on the upper right hand corner of the screen. And then for those that do not like Facebook, that do not like Discord, I also have Telegram. It's still maturing, this one. It's what it is. But I do announce everything there also. I have, if you want to go that extra mile and support us, then you can either support us on Patreon or on Ko-fi. Both of them are identical. You have lots of videos. In this case, there is 101, and I didn't plan this. It's what was from last month. This month I haven't uploaded the videos yet, but there are a couple that I need to upload. But normally I wait and then I upload everything and update everything in one go, and you get access to everything in one go. Because if I do them every week, it's too much work. While if I do them in one go, it's quicker. So there is Patreon and Coffee, as I said. For this series and the book series, etc., I also have this page, the Amiga 68K Assembly Programming, where you get links to most of the things that are helpful for somebody that is beginning. Okay, so this is you don't get everything, so don't think that I have all the links outside there into this page. No, but what I think is useful for beginners, I put it here. We are using Asm Pro, as you know, for the series on the Amiga, but we are also using Easy68K that runs on Windows, just to demonstrate the 68,000 instruction set. I do like this tool. It's good for testing the instructions or something quick. But most of the time I am showing the examples on the Amiga, not on this. However, when something is not clear or once, we can also show it on this one, or we see the behavior on this one also. Let's say that. For those that use Linux, there is the 68,000 simulator that you can use to simulate the 68,000. I'm just going to put the links again to these two, as I always do. That's the Easy68K, and this is the for the Linux version or Mac. So let's switch to the Amiga. Okay, I need to be on the Amiga too. Now this is not right. Read, and we need to go from the beginning. MoveM. So last week we started talking about the MoveM instruction. Okay, we did cover parts of it, but today I'm going to give you a, let's say, show you pitfalls that you might have fallen or you can fall into if you are not careful. Okay, so let's go to Acrobat, and I'm going to show you the MoveM. First of all, okay, I'm going to change a bit the screen to close up. So I said in some other stream, I can't remember what I recommended, but I recommended this book. Okay, so I have a copy of it here and another copy of it in UK. This book is written by someone that teaches or used to teach in the Middlesbrough University. When you look for the instruction set on the internet, okay, and you have links of it on my page, you come to a PDF that is online and is called the 68,000 instruction set, and that PDF is the Appendix D of this book. So you can see it says 68,000 instruction set, and you can see if I go at the top of this page of the book, I will show it to you in a minute. So if I go fit to one page, and I'll show you the book. So that and this are the same. Okay, so you're seeing that now close up, and you should see the same thing. Okay, hence the while I like this book also. The other thing is at the back, I mean, not always you find the floppy, but mine, both of them has got the floppy. Okay, has got a floppy, which is a simulator of the 68,000 on the PC, but in DOS. Okay, so unfortunately you need DOS for this, because when it was written. When I say DOS, it needs Windows 3.1, I think. I can't remember. But yeah, it's what he has wrote himself. So back to the Acrobat, and back to the MoveM instruction. Let's so the MoveM instruction. Okay, you can see the book says repeat until all registers in the list are moved, and basically you have the source, which is the whatever that is, and goes into the destination registers, or same thing, source registers into a destination location. Okay, that's how you have to interpret the book. It's a bit misleading the way this is done, I have to say, because source on 68,000 is always on the left side, not on the right side, but it's on the right side, like that's how the book has represented this. But it's not a big issue. Again, here are examples of the move instruction. Okay, MoveM, instruction, effective address into a register list, and register list into an effective address. And here there are some examples. Okay, we are moving a number of registers into this memory location. We are moving what is in A5, what at the address of A5, what is in there, to these address registers. We are moving, and this is weird now, what's in the stack. Remember, A7 is the stack. Into the data registers and address registers, and we are moving the registers into the stack, and that's, remember, the minus is when you are moving to, so this because the stack grows downwards. It can only be size and long word. Okay, here we have the description, which I will skip a bit. And you can see that none of the flags are affected. Okay, that's the PDF is on my link page. Okay, the page that I always say that, and so you can find this PDF. But if you look for 68,000 instruction set on the internet, this is normally what you find, and this is related to the book that I just said. Let's go back to the Amiga. Now, this example, there are some things that I need you to I need to make you aware of. Okay, so let's execute it. So I did A to show you that it's it doesn't have errors, and then we do AD. And we go into debug mode. So the first instruction, we haven't really covered it, but what it does, it clears a register, and we're clearing it long. So did 0 and the 1, we cleared them. Okay, now we're moving the number, okay, 1 2 3 4 5 6 7 8 into label, and notice label has got 3 long words, let's say that, of 0. So we move that into label. Now here is a pitfall. Okay, what do you think is going to be copied into D0 and D1? So look what's going to happen to D0 and D1 as soon as I tell it to continue down. If you notice, D0 is now we are copying so the move.long, we copied that value where label is. Okay, now the address at label, okay, we're copying the contents to the 0 and the 1. Okay, so I'm going to start the example again from the beginning. So AD. So we moved that number where label is. Now we are going to move what's in label into the 0 and the 1. Okay, notice. Hello JJ Ballon, good evening, welcome to the stream. So now when I execute this command, we're going to copy the 2 long words that start at label. And right now we have the 1 2 3 4 5 6 7 8, okay, and then the second long word is 0. Okay, I'm just going to run the same example again and removing the second one. So now we're going to move at label, okay, that number. Okay, so we're going to copy that number to where the label address is, and then we're going to copy this number to label plus 4, because remember 4 bytes are a long word. So we copied that into the first 2 or the first, actually, let's say 8 bytes, okay, where that start at label. So now when we do MoveM, okay, we copy those 8, okay, into the 0 and the 1. And you can see the 0 and the 1 copied. Now, same thing. I'm just going to go to the editor and edit and remove this. and assemble and run it again. Now, what I didn't mention is that many times you can forget to do that +4, okay? So basically what you will be doing is overwriting what there is at the address where label is. We copied those 8 bytes into the 2 long words that start at label. Now we're doing again copy what is at label, and notice now that the 0 and the 1 has got the values that we copied at label. But when we do the opposite now, we're copying, okay, and notice it's a move.word, not a move.long. The 0 to the 1 into label, okay? I can show you. To be fair, this example, I just realized that, so when I tested it, this escaped me. I just realized that nothing will change. I should have had label 2, okay? So I'm just going to correct it in a way. This escaped me, literally escaped me when I was doing the example. Let me correct it here. Label 2. So let's read the file again. Continue. So I created another label, label 2. Oh, I forgot to edit the label. Okay, so let's do that and let's do that. AD. So we copied these 2 long words where label is, okay? And then we copied them into the registers 0 and the 1. Now we're going to move the words, okay, of the 0 and the 1 into label 2, okay? To demonstrate that what was copied, so I do m label 2, and you should see this is all that was copied. Then we have 0, so it's rubbish after that, okay? So 5, 6, 7, 8, and CD and EF. So 5, 6, 7, 8, CD, EF. Okay, so we took the the words of these 2 long words and copied them into where label 2 is. If we did, and I'm just going to run it again, but commenting something out, because it could be misleading. Notice when you start the debugger, it remembers what values you had before. Okay, but we are going to clear, and this could be because of the way the memory is, because we initialized it and then it's still remember what it is. We cleared the 0. We moved a value into the 0. Sorry, into a value into label. But then when we move label the 0 and the 1, okay, notice that what actually is copied, okay, is what's in the second long word, which is the 0, because we didn't initialize it. Okay, it can confuse you sometimes, this, especially if you do this, especially if you have this mistake and you forget this, which can happen. This will really confuse you. You will see that you have the second value, not the first one, and the one is 0 because we haven't really initialized it. So you need to be careful of that +4. And also the opposite, when you're moving from the register to the label, you need to make sure that the size is correct. In this case, we copied a word, so we can only, well, label to is copy 4 bytes basically. While I'm at it, you can see the section directive. I have already mentioned it. The Amiga has 2 types of memory, okay, where the graphic chip CD memory is called chip memory, and any other data that the graphics chips do not see is called fast RAM or slow mem, depending on the type of expansion, but I'm not going to go there. This, you name the section directive, take a label, a name, so you're labeling the section as my data, okay, and then you're telling it that it's data and it is chip. The _C is chip data, so it's where the graphics chips is what the graphic chips can see. This is similar to, in a way, just for those that are C64 oriented or 6502 oriented with the Commodore 64, the VIC2 chip can only see banks of 16K of RAM. The chips on the Amiga, the graphic chips on the Amiga, and sound and the graphic chips and sound basically can only see a certain part of the memory of the Amiga, which is called the chip RAM, and that is why the _C. So we are indicating its data and its chip RAM. I didn't specify a section on top, but normally you do, okay? And there are certain rules between sections. This is not the same as blocks in the 8086, just to be clear, Dr. Honey, if you're listening, but is to differentiate. Hello, Fewbit. Welcome to the stream. I'm not sure if, I believe you are on the file because it recognized you and it did the shout out for you. So yeah, the bot is working. Old school coder. So So yeah, the section directive is to distinguish the types of memory that the Amiga have. A section is also is not in a way limited, but there are instructions that can only see a certain part of the section. Let's say that can only jump to a certain part of a section, which I will not go there. But yeah, and there are instructions that are for example, the JSR instruction can see the whole amount of memory, while the branch to subroutine, so JSR is jump to subroutine, and that can see the whole of the memory of the Amiga, and branch to subroutine can only see any routine which is in the section, which there's a difference, okay? But we will come into these things later on. Anyway, that was the MoveM command. Continue. And now the move quick. I know we did this, but I didn't explain. Oops. Some things about the move quick. We used it, but certain things were skipped because this example was I was supposed to do it last week, but I skipped it. So, first of all, notice that it gave me a warning. Okay? It's not an issue, it's a warning to tell me something about the move quick, which I will explain in a minute. So, first, let's see it. So, we're going to initialize all these registers with long words of FFs. Okay, so you can see that D5 from D0 to D5 are all FFs. Okay, now move quick, and move quick doesn't take a size. There is no B, there is no W. It's always long. Why I'm saying this? Because as soon as I do move quick, immediate a value of 12 into the 0, you can see it moved 12 and everything else is 0. Same for the next one in the 1, and same for the next one in the 2. Now, move quick can only take a value between -1 to 8 to +1 to 7. The first three numbers that we did were all positive numbers. Now we're going to do negative numbers and see what happens. So we are moving 8, 0. Okay, 8, 0 has got the sign bit or the most significant bit in the byte set. So when we move 80, actually the value moved into the tree is all F's and the 80. So every byte, okay, becomes FF, and it takes the sign bit with it. So if you notice, the first 3 bytes are FF. Okay, same for the next value, which was 8F, and then of course we have FF, and because FF, it does them all as FFs. I could have cleared it, so I could have done. Actually, let's do it here because I'm quicker. That's why I'm saying this. And then I read the file again. I could have done these as 0 actually. Save it and read it again. So now the 3, the 4, and the 5, I initialize them with zeros. Okay, so it will be more evident. Okay, and now you will see that it fills up everything with Fs for all 3. Okay, so the sign bit is repeated through all the other bits, basically, for the whole long word. Now, I'm just going to show you these 3. And notice that I specified a size. And you can see what the assembler said. Illegal size, out of range. It still means illegal size, okay? But because we specified a long word, okay? So it's not illegal size because MoveQuick can take a long word, but it is out of range because we specified a number which is higher than +127 or -128. Hence, it gave those errors. Notice also where I told you the warning. What it's telling me there is that I have used MoveQuick, but because MoveQuick, the sign bit is extended, is telling me about the extended sign. So be careful to be careful about my my code. Maybe I should have not my code should maybe I should be careful not to exceed 127. So that's why there is this warning, because maybe I wanted 128, but not in a negative one. So I didn't mean -128, but I needed 128 positive, but it's saying that it doesn't handle it. So that's what it means, that warning. So it's not an error, but it's a warning from the assembler. The last bit, what do you think will happen here by when I do A, when I tell it to assemble? Basically, MoveQuick only works on data registers, so not on address registers. So this is something that you can also maybe make mistake, and then you realize you should use a data register, or you find another way of how to initialize it, basically. So I'm just going to jump a little bit on the on Acrobat. Okay, and I'm just going to find MoveQuick. You can see that its size is always long word, okay, and that the MoveQuick is always against a data register. I wanted to come here to show you to explain this, okay? this sentence. Move.byte immediate 12,0 is not the same as MoveQuick 12,0. One, you're only affecting the first 8 bits of registered 0, while the other one, you're affecting the whole 32 bits of registered 0. And that is the difference between move.byte and MoveQuick. Of course, MoveQuick is a quick instruction, is faster. Okay, so when you have smaller numbers that are okay within the range of from 0 to 1 to 7, I'm talking positive right now, it's better to use that, but you need to keep in mind the MoveQuick instruction. Now, last week I told you that Docster, okay, used MoveQuick on strings, okay, text. A string can be more than 1 to 8 characters, so MoveQuick is really not the right one to use. Hence, you have to be careful with MoveQuick. Yes, it's faster, but it can also give you headaches. So, back to the Amiga. And we read the next one. LEA. We also talked about LEA, but so this is an example that Docster did. Okay. Also notice that in this example, okay, there are no section directives. Now, let's execute it. And he's working on a string. We did cover basically this last week, but I'm showing it because Docster did it, and you know, it's I'm using some of the stuff that he did because he helped me out, so it's fair to show it. So LEA text, 80. What we are doing is having the address of where text is into 80. Now, this instruction can be changed, okay, to make it more efficient, because we are talking in the same section. So I will tell you into how we can make it more efficient in this case. But for now, we have the address into 80, okay? And you can see it there highlighted in 80, the address where text is. Also notice that we are using not chipmem but fastmem because of the address where we are. Okay, the 4018251C is a fastmem address. So then we're getting the H into the 0, the capital letter H into the 0, and we increment 80. So you will see that 80 right now ends with 1C, is going to be 1D. Okay, and we get 48 into the 0. Again, we increment 80, and the 0 has 65, which is for the E letter. But 80 now points to the letter L, okay, in the string. Now, what I was saying about how to make it faster is by using PC. That means we're going to take this relative to where we are. and you're going to see a change into the way the what address is loaded into 80. So it's the same address, sorry, not the address is but the size of in terms of how much space it takes in memory, LEA text PC, 80. I should have shown you that actually before. So let me do it as it was. Okay, let's assemble it. And now I'm going, so instead of using AD, I'm just going to use D by itself. And you can see that it's taking, so LEA, okay, is the 41F9. That's the opcode for LEA, okay? And then we have the address that we are trying to move. And notice that in total, okay, it is is 6 bytes, right? As it is. So if I do, you see, assemble it and now do D, notice that from 6 bytes it went into 4. So we saved 2 bytes. Also the address, okay, the what it stored, so we have the address 401825, okay, 51E, okay, that's the address, but what is stored is the offset, which is 0008 bytes away from where we are. That's what it meant, what it means. Hence it's shorter, no? So from 6 bytes we save 2 bytes. Also it's faster in execution, takes less cycles. That's basically it. So next example. So this one, we're just going to see how the addresses are. I mean, I already explained the PC, but you're going to see it in a better way, let's say that. So we are initializing the address registers with to 0, okay, the A1 and A2. And notice I'm not using MoveQuick because I can't, but I have to use the move.long. Now I'm getting the address of loop 1 into A1, and you can see the long value into A1. No op means do nothing, okay, like the 6502, no operation, okay, it's just to waste time. There it is. And then we are going to come to the next no op, which is labeled loop 1, and the address should match that of, so the PC, okay, this one should match what is in A1. And you can see that they are the same. We continue. Notice the address of the no op which is at program counter is saying it's 2130. Okay, so A2 should have this number now. To 130, as you can see there. Now, of course, what I had explained earlier, come on. So we initialize again the address registers to 0. Now look what's going to happen to A1. It's still showing that value in the debug because that's the actual address that we really want. So A1 does hold the value of the address of loop 1. Okay, so just because we inserted the PC, it doesn't mean something changed. And same thing for A2. You can see it here that it's still the same, but where we will see the actual difference. Oh, I'm pressing F1. I'm saying why didn't if I do this. So notice, remember it can go plus 32767 and minus 32768. In this case, okay, you can see the 0004. So it's saying the offset is 4 bytes away, but A1 still have the address that, I mean, so basically it's calculating from where it is plus 4 and it gets this address basically. It's not really plus 4 because it's also adding the instruction length, but you as offset is 4. Because to 8, so the next instruction is to 8 plus 4, because I was set. Remember, the program counter is always the next instruction. So same thing for the last LEA, okay? But this one, the last LEA, is pointing to this no-op, okay? Where we have the 2128, okay? So 2128 is minus, I don't know, whatever that is, FC minus 4 also, okay? So it's more, no? Because it would be pointing here 3 4 and it needs to go to 2e. So is it? Or it will be pointing here 3 0 and minus 4. Yeah. Now it will be pointing here 4 5 FA and then it does minus 4. Yeah. I guess that's how it's calculated. Anyway, you get the gist of it. It's confusing me the way it's represented, to be honest. Yeah, it is 4 bytes from here. Yeah. Okay, just calculating in my head. Anyway, that's regarding the LEA instruction. Continue. Swap. This instruction, you'll use it a lot. And it also has some good advantages. First of all, swap only works on words, okay? And back to the book. Swap. You can see that size is word, okay? And it works on the whole long word by swapping the upper word with the lower word and vice versa. So it's very simple. The V flag and the carry flag are cleared, and the 0 flag and the M flag are set accordingly. Now, if the value is 0, then it's a 0. If it's if the extended bit is set, it will be set. So back to the Amiga. Let's assemble it and debug it. So we're moving this number into the 0. And notice, hello, Care Unix, I guess I have to say. Welcome to the stream. I'm doing assembly 68,000 for the Amiga. Actually, it's 68,000, but I'm using the Amiga as an example to show the 68,000. But of course, mainly what I do is related to the Amiga. But however, this series that I'm doing about the 68,000 is all can be applied to any other machine that uses the 68,000 CPU. So, hello, Tits Trinity. I mean, I think this is very basic for you, Tits Trinity. Ah, I see. So you have an idea of it. So basically, both of you know 68,000 well. Then I'm referring to Care Unix and Tits Trinity. Yeah. So we have moved that number into the 0. And now look the values that we have into the 0, how they are going to be changed. So the high word is going to be swapped with the low word, and the low word goes into the high word. As you can see, we have FF778234 now, which is what it should be. Now we're moving, okay, a word into the 2. So the 2 has the number 7654. Swap, remember, as I said, will work always on on words, but on the whole 32 bits. So it's still going to swap, as you saw, the high word with the low word and the low word with the high word. I mean, they change position. However, swap has got quite a number of useful things, especially in the Amiga world. And the next example is actually for something that you do a lot on the Amiga. It's this example is quite, let's say, you write the same routine, not on the same registers, but many times for other things. And so it's a common example. Notice also that I specify the section directives. One, RTS is return. Yes. Notice I have two section directives. One to say that my code is public, so if there is fastmem, it goes into the fastmem. If there isn't, it means it goes into chipmem. But I specified that the data is in chipmem. So my chip data, the second section, and data underscore C, which means put my data in chip memory. So we have the address of image into the 0. As you can see, it's 7D110. You can tell this is a chipmem. The address is very low. And then we are going to move, we're going to copy our image that we have down here, okay, of this size, into the address pointers that we have here that the Amiga uses. These are the bit plane pointers for the 3-bit plane pointers, let's say, because it's a 3-bit plane, so 8 colors for the Amiga, and these are the actual registers for it. Down here we have a block defined, which is you remember our screen is 320 by 256, but we work in bytes, so the 320 is divided by 8 times 256, and since we have, that's 1-bit plane, and since we have 3-bit planes, times 3, no? And we are initializing it with 0. That's what we are doing here. So, and we have the data registers, sorry, the bit plane registers. You can see the E0, E2, E4, E6, E8, EA, and you know the bit plane pointers take a long address. I mean, the bit plane pointer is a long address, but we need to divide it in two, because we can only specify, a register can only hold, is always a word, so we need to specify the high word here and the low word here for the first bit plane, and it continues like that. So we get the address of the bit plane area where we have the registers into 80. Then we initialize using MoveQ. We have 3 bit planes, but remember we go to 0, not to 1. So 3 minus 1, and we initialize the D7 as a counter, as our counter. Now we take the address that we have in the 0, okay, which is the 7D110, and we copy the lower word into 80 but offset 6, so we are copying here, okay, this part where we have these zeros. Then we swap, so then we're going to get the word, but we're only going to have this 0007, okay, and we are going to copy it here, okay. So we swapped. You can see it swapped itself. So the 0007 is in the low word now, and now we're going to copy that at offset 2, so here from where 80 is, okay, and we're going to copy the 0007. We swap it back to what it was. Why? Because we need to do the next bit plane, so we cannot leave it, and this is a mistake. Sometimes you forget this swap here. So that is something that I've seen. Then, of course, to get the next bit plane pointer, okay, we need to add the width of the screen by the height in bytes. So 320/8 times 256, and we add it to the 0, okay. Then we add also, so we did these two, no? These first define constant word, these first two lines. Now we need to do these two for bit plane 2. So we were here, we need to move down here. So we need to add 8 to 80. So we do that. And now the 7, which is our counter, okay, is going to be decremented, and then we jump back to where loop is. And we continue to do this for 3 times. This is the second time. And the last one now, D7, if you load, yeah, it's a loop. And when you do a move, I'm trying to understand. You always specify. We're working with words here, so no, it won't work. What you said, having one swap. What you would do? You only need one swap if you're not in a loop. But then, if you need to use the value in the 0 again, you might be in trouble. So it's good to put it back as it was. Maybe you have some other calculation that you need to do. So it depends. If you don't, then you just need one swap. If it's just one bit plane, let's say that. So now the 7 is 0 and we exit our loop. Okay? To show you, so if we do M image, you can see that the address of image is 7D110. Okay? And if we do M bit plane pointers, you can see first we see the 00E0, and then we should see the 0007. So 0007, there you go. And then the D110 So first we see the 00 E2 and then the D1 and D10 of the first bit plane. And we continue this continued like this. So 00 E4, what we have here, okay, and now the value of we see the population, the how we populate it, not the population, uh, at this word. Oops, sorry, because I did escape. So we're going to see the value that we have put in E4, which is still 0007, but then E6 will have a different value, which is F910. So the actual address of the second bit plane is 7F910. And then we see the third one. So it's this one is 0008, the address, and then 2110. I just want to show the same thing. You can remove this and do this using the LEA. Oops. Sorry, not. I did this to show you that with LEA you cannot use a data register, but you have always you need to use always an address register. That's why I had to use the move.long, and same thing. It's telling you that LEA, the assembler is telling you that it always needs an address register. This is, I mean, you do these mistakes in the beginning because you forgot these things, but the assembler is quite helpful. So the right way of doing it, because we are using the 0. Did it wrongly? Is this? If we're using an address register, then it would be fine to use LEA, and actually the best, this will not work if, let's say, we're using A1. Let's just do, I'm not going, of course the program will fail if I use A1, but I just want to show you something. Oh, needs to be this one. Okay, so the LEA instruction is fine, okay, but the assembler will still give me an error because we have two different sections. So the PC, okay, the relative mode will only work within the same section. Okay, so this addressing mode will only work in the same section, not in different sections. It will be fine like this. As you see. These are common mistakes, let's say that. So yeah, in the beginning you do them quite a bit, and sometimes you still do them, so it's not the end of the world, the assembler tells you so. So yeah. Oops. Was that example 2 that I did? Oh, yeah. The exchange instruction. So basically, it exchanged one register to the other. Okay. So, and actually, let's do one thing. I should do two things actually. One, show you LEA. It's not going to find it as I want, so let's find it ourselves. There you go. So you can see it only works with address register. So, and it affects the whole 32-bit because address registers are 32-bit. You can see it takes the PC, what I was saying, and you can also use other type of addressing modes. But remember, it's a different way. So you can write, this is because you're seeing it here and I don't want you to get confused. This is the new way of writing it, okay? Let's say that when the 68020 came in, this is how they started writing the LEA instruction which is relative. But before, when it was just 68,000, and this is why I'm using that mode, because this is how I know it. You can use the table bracket PC bracket, while you cannot. The new way is table and PC together in the brackets. It doesn't make difference. The assembler knows both, so it's not an issue. But as I said, be careful when there is a section directive because it will not work. Maybe it works on other machines. I do not know, to be honest. I doubt it. Unless the data is near. But when you're using a section directive, you are saying this block of memory is somewhere and the other block of memory is somewhere. So it's very difficult that they will be close. And the relative is only plus 22767 and minus 22768. So unless the blocks are very close to each other, it will not work. But anyway. You can see that it doesn't support data registers. Referring to source. And these are all the addressing mode that it supports. Now we're doing exchange. So basically, the exchange is a register. So we're swapping basically the registers, the value in a register. So the 3 goes into the 4 goes into the 3. And it works on address and data registers. Size is always long word, okay? You cannot do exchange.w or .byte. Just to be clear. So let's see it in operation. So we are initializing these registers with these values. So D0, D1, H0, and A1. We initialize them. Okay, and now we're going to see the swapping between them. So D0 and D1, you can see we swap them. H0 and A1. Okay, so these two here, where we have 4s and 5s. And now D0 and A1. So D0 and A1. Okay, and H0 and D1. So I think it's a self-explanatory instruction and it's quite an easy one. So yeah, not much really to say on this one. We're going to see the add instruction. We already have seen it, but now I'm covering it in terms of, you know, all instructions. I mean, as an instruction, because before we were just touching the surface of it. Yeah. So we have we're going to move a word into the 0, and you can see it. And then we're moving another word. Funny enough, I chose 101 into the 1. And we're going to move another long word into the 2. And now we're seeing the what the instruction does. So the source is the 1, where we have the 101, and is going to be added to D0, okay, where we have the 1000, but the add is a byte, not a word. So actually what we are adding is the 01, okay, with the 00. And you can see that D0 became 1001. But it was added, okay. We worked only on the lowest byte. Now we're going to add D1 and D2, okay, and this time it's a word. So D2 has got that long number, the 1 2 3 4 5 6 7 8, okay, and the 0 now has the 1001, but we are only going to work, so what we are going to add is the 1001, sorry, because the 2 is the source, the 5 6 7 8 with the 1001, and we have that, and the value will be stored into the 0, and there you go. Sorry, we were working with long word, not with word. For some reason I was looking at the instruction below. So sorry, we were using the 2, so the whole number, the 1 2 3 4 5 6 7 8, and we added the 1001 to it, and hence the value that we have in the 0. Now we're going to work on a word. Okay, so D1, the word is 0, 1, or 1. Okay, and D2, okay, the word is 5, 6, 7, 8. And the result will be stored in D2. And as you can see, that's the addition of those two numbers. We are going to move a byte into the 0 now, the low byte. So the 0 is going to end with FF, as you see there. And now we're going to add D2, okay, which is a byte. We're working on bytes now. So D2, which has got the value of 79, with the 0, which we have the value of FF, okay? And of course, this is an overflow, okay? So the V flag will be set. And you can see that the value 7, 7, 8, I have a, this is wrong. I put 7, 7 for some reason. But 7, 8, okay? And yeah, the actual calculation is wrong because we overflowed. So something to keep an eye on while we are at it. Let me find the add. Oh. So for the add instruction, first of all, there is but I'm pressing wrong. So although in the assembler we use add, the assembler will convert it depending on what we are using. Okay, just making sure that I am covering them all. So the first one is add, okay, and add is an address to the data register or a data register to an address. Okay, so that is add. We always write add in the 68,000, but it will be changed depending on what we are actually doing by the assembler. So let's say the AI, as we say today in the modern world, okay, the AI of the assembler will change it. So when we do when we are adding to an address, okay, it is actually the instruction is add a, okay. So the destination is an address. When we are adding an immediate value, so a value, it's add I, okay. So we don't write add I, okay, we just write add and we specify the value, but the assembler converts it, the AI, I'm enjoying this word right now, the AI of the assembler will convert it into add I. Add quick, I suggest you write add quick, okay. Don't let the assembler does optimize to add quick, okay, but I prefer to write it when I need it. and then there is addx for the extended bit. So this you have to write for the assembler to know that you are working with the extended bit. You need to say addx. That's all about the add instruction. Let's go back to the Amiga, and I'm getting thirsty. So yeah, Hound Dog, thank you. Done, as you saw. So let's do the next example. Did I do some cuckoo here? I'm seeing that the last, before the RTS, I'm seeing that move KJD. What the heck? I think this is example I made some cuckoo in it. I'm just going to do this and still okay. I think I wanted to demonstrate something more than that. Yeah, KJD. No, I think you know, when we are doing several things, you have a window open on one side, let's say on one screen, and another one on the other, and you switch from one to the other, and you forget, and then you type something, and then you save, and I think this is what happened, seeing KJD there. But anyway, definitely they are not let's say instructions of the assembler. Yeah, it's a feature, not a bug. Neither one nor the other. It's a typo. Anyway, so we're moving a word with the value of 102 into D1. Okay, we're moving a long word. And notice when I'm reading the instructions, I always read the size. Because when you have issues, learn to read the size, not just move.long, say it, so that when if you have issues, you have registered that you are working on long. Okay, same if it's word or byte. We have moved a value in the 2. To be honest, I don't know if this example is going to work or not, because honestly I think I had other things in my head when I was doing it, and then I must have copy and paste or something like that, and I googled it. I ruined it. And here we have a move.long on an address. So the address is now 00400. And then we're doing, so notice I'm using add a, not add, but you could use add, okay, in this case. And we are going to add D1 with 80, okay? And its destination is 80, so that's why it's add a. Okay, so we are working with addresses, so the instruction, I mean the destination is an address, so that's why you use add a. Now we're going to use word. Okay, so and we are going to use a destination is also an address, and this time it's D2, so the 6678 with the A1, which is the 1000 in A1. We did D2 5678 with A1. I forgot what was in A1 though. 1000. So from 5678 it became 6678. Yeah. Okay. And now we're doing an add a long, so with an immediate value. So whatever is in A1, this so it is the 6768, but long word plus the 1234. Okay, and that gives us 78 AC. To be honest, I think I had something else in mind, but yeah, it's what it is. I did this quite a while, so I really forgot what I had in mind. That was so yeah. 3. AD. So we're moving a word, the 1, 2, 3, 4 into the 0. Notice that the high word is 1, 2, 3, 4 also, funny enough. But we are working with a word. Okay. Then we have the add I dot byte. We normally do not write the add I. Okay, I'm just showing you that the assembler understands add and add I at the same time. So we added the 34 with what was in the 0, but working on a byte. Okay. Then we are going to work with a word by adding 200 to the 0. And you can see it incremented. And now we are going to add a value of 1000, always hex, long into the 0. And that's basically it. Again, we're going to move a byte into the 0. So we moved 12, but the D0 is still what we had before. It's a good habit to clear the registers before doing things. The assembler here is remembering what we had. I have to say that not all assemblers do this. So in this case, this is the one on the Amiga, the Asim Pro, still remembers what we had before. But the one, if you use the extension of Visual Code, sorry, it will not remember the values. But anyway, here we are just using the assembler to learn the instructions basically. And these are examples that you will not be using in your code just like that without any initialization, nothing. So yeah. We're going to use add quick, and notice no size specified. So we're going to add 7 to what we have in the 0. And you can see it became 19. Then we have move long, again the 400 400 into 80, and now again the add quick of 6 and 8. One is on 80 and one is on the 0. So it became 004000406. And add quick into, we added 8 into the 0. What I want to show you, because actually I skipped it. Acrobat. So it's not doing scrolling. I have to scrolling. Yeah. So at quick, it takes, so this is different than move now. You were in a break. It takes byte, word, and long word. But the range is from 1 to 8 at quick. So it's different than move, okay? Don't assume that you have plus 1 to 7 and minus 1 to 8. At quick works only from 1 to 8. That's the immediate data range of it. This is a very quick instruction. It's only 2 bytes because these values are within the instruction, so it's not going to waste another byte for what value you specified. But it can work on all sizes. So yeah, that's the difference between move quick in the move instruction and add quick in the add instruction, let's say that, or add category. So I think, yeah, this is a Docster example. I don't think I corrected this one of his, so I'm just leaving it as it is. But if there are some typos or things like that, I don't recall correcting this, because when I arrived at this, I didn't, something has happened, and I remember I didn't go back to it. which is a shame. So we are moving a value into, and my value is, let me, we have a long word, okay, in memory. We're pointing to it by my value, and we're taking this value and putting it into 80, basically. And we're adding at quick 8 to whatever there is in a 0. Sorry, to 80. So 80, really? Hold on. I think I better check this example. So at my value, we have 1. And we are loading. Okay. So there is 1 in my value. So we're copying 1 into 80. And then we're adding 8 to the value of 80. So we end up with 9. And then we move that value that we have in 80 into my value. So then we store 9 there. Then we are taking what we have in at my value and putting it again into A1. So there you go, is the 9 again into A1. Then we are going to do a move dot long of 1 into the 0. So sorry, I skipped an instruction. We add what we have in A0 with A1 and we add it up with 12. And now we are going to do this instruction of move.long 1, the 0. So we're going to initialize the 0 with 1. And then we're going to add what is in the 0 to A1. And the A1 has the value of 12, so it's going to become 13. And that's it. This is like a summary of what the examples of Docster are many times a summary of what I cover more than anything else, because I do go into more detail than maybe what he did. But his examples are quite good, and further down there is much more than what we are seeing here. Guys, thank you very much for being here, listening to me, talking about the 68,000. I'll see you next week. It's Easter. I should have the next series of examples for the next episode. And yeah, it will be same time, same stream, and we continue talking about the 68,000. So have a lovely week, guys, and see you next Sunday. Bye bye.